All right, guys, let's finish the notes. This will be our last set of notes for the whole year. After this, we'll review some, and we'll have our test, and that'll give us several days to do some things. We'll have a couple of days of brain stretching. I've been calling it problem solving in chemistry, and then we'll start reviewing in earnest for the semester exam. So the last set of notes that I want to talk about just briefly. We won't spend a lot of time talking about this. You'll cover this more in depth in later classes if you take more chemistry. We'll talk about buffers. So this is our last set of notes. And to understand the buffer, first we have to talk about this thing called the common ion effect. And so we're looking at an equilibrium, and on each side of the arrows, so here's our equilibrium arrows, right? On the reactant side and on the product side, we have this ion, the acetate ion. Notice that in one side, he's participated in a molecule, right? He's in the acetic acid molecule here. But as the acid molecule is added to water and allowed to sit, we know that we've got an equilibrium situation. Now, it does favor the reactants, because the exponent is negative, right? It's less than 1, the value of K, but there will be some products present there. So the equilibrium here contains one side of the scale that's got the acid molecule where the ion is bound up, right? Bonded to the H+. And then on the other side of the scale, he's free. So if we were to make a mixture, acetic acid and sodium acetate, we would be increasing the amount of the acetate ion, because sodium acetate, if we check our solubility rules, it's soluble. So we'll have sodium and acetate. So effectively, what we're doing is we are creating what is called a buffer. And a chemical buffer is a specific kind of mixture. A buffer has to be a mixture of a weak acid and its conjugate base, or you could have a weak base with its conjugate acid. We'll focus mostly on the weak acid mixtures. All right, so what that does is it gives us more of this concentration of the acetate ion, so that we have a presence on both sides. So remember we said that this particular equilibrium would favor the reactants, which means there's not very much products. But if we add some product, then we would have a mixture where both sides of that equilibrium were fairly well represented. And so then the question down here becomes about the activity of the buffer. So if we added some acid, that means that we would be increasing the H+ concentration. And this acid doesn't need to be acetic acid. It could be any acid. It could be a strong acid. If we add some acid, we'll increase the concentration of the H+, and the equilibrium will shift accordingly to the left to use up the acid that we added. And then if we consider what would happen if we added some base, this one's less obvious because there's not an OH minus in the equilibrium, but it would react with the H+ and thereby lower the concentration of the H+. And if we lower the concentration of the H+, then we will shift the equilibrium to the right. So this is the basic underlying mechanism of a buffer. Buffers are chemical solutions. They're mixtures that I think we'll define this maybe here on the next slide, that resists a change in pH. And the reason that it can is because of this equilibrium that we set up when we mix a weak acid with its conjugate base. And then the counter ion here to pair with the conjugate base. as long as that is the conjugate of a strong base, and this is the conjugate of the weak acid in the mixture, then this will work. We wouldn't want to use the conjugate of like a weak base, because then that's going to have an impact on the pH as well. So we use something like sodium acetate. In the demo that I did in class, I don't even know how long ago now, a few weeks ago. Oh, excuse me. A couple of, I don't know, a week ago, several days ago, whenever it was, when I showed you all of the beakers with the different colors of solutions when I mixed the pH indicators in there. And we said it looked kind of like egg, when you dye eggs at Easter. We had a pink one and a yellow one and a green one and a blue one. So in the blue, in the beaker that turned the indicators blue, I used either sodium acetate or potassium acetate, depending on which class you are in. I ran out of sodium acetate pretty early on, but potassium acetate would work fine because potassium is the conjugate of the strong base potassium hydroxide. So again, it would have no impact on the pH there. So the big important thing to understand about a buffer so far on this page is right here. It's a mixture of a weak acid with its conjugate base. And what that does is, using the principles here of Le Chatelier, it creates a solution that resists change in pH, and it's because of the common ion effect. Think Le Chatelier. We look at a buffer zone, a region on the pH scale where it is effective, and it is within 1 pH unit on either side of the pKa or the pKb. So I'm going to talk about that just a second before we move on. pKa. Okay, so Ka is 1.8 times 10 to the minus 5. All right, so the pKa for acetic acid would simply be the negative log of the Ka. Remember, we talked in previous notes that whenever you have the P of something, it's just taking the negative log of whatever that something is, right? When we have pH, it's the negative log of H+. We also talked about the POH, which is the negative log of the OH- concentrations. All right, so now we have a new guy, pKa, pKb. There's other P things. It's the negative log of those equilibrium constants. And the only reason why we would do this is because it shows us where the buffer would be effective. So for acetic acid, we would find that the pKa would be negative log of 1.8 times 10 to the minus 5. I'll get your calculators out and punch that in. See if you can beat me. I don't know where my calculator is. All right, I got that value to be 4.74. All right, so this is on the pH scale, 4.74. So that means that an acetic acid buffer would have a buffer zone from 4.74 minus 1 to 4.74 plus 1. So this would be effective at the pH range 3.74 to 5.74. And so what that means is that within that small window, as long as you don't add, an extremely large amount of a strong acid or a strong base, as long as you keep it within that window, then the buffer is going to be able to sort of accommodate whatever you've added to the solution. And the pH won't change as drastically as it would if you didn't have the buffer present. All right, so when you look at, say, a titration curve, normally we don't have a flat spot like this, that's so wide. But notice what happens is, so this is some weak acid. It could probably be acetic acid, perhaps, if the pKa 4.74, and maybe it's a little bit lower than that. But this would be basically what would happen in a titration. If you had a buffer present, you would be titrating, so it looks like our analyte is acidic, and we're adding a base, right, because we're increasing the pH. Notice that in this entire window right here, the pH doesn't change that much. Now, of course, it's certainly possible to overwhelm the buffer and get outside of that pH range. Buffers aren't magic, but what it does is it resists the change of pH in this region. And there are some reasons, some real-world applications that we would care very much to have a good buffer system. But let me just finish on this slide, and then we'll move on and talk about that. So it has a window, a range where it's effective. And I think this picture here is to kind of show, like buffer zones around like political states. You guys have probably studied this, regions where, there's like some safety in between two warring nations. I'm not exactly as up to date on where this might be going on, but I'm sure you guys know exactly what some good examples of that in the real world. But in chemistry, the way we make a buffer is we mix a weak acid or a weak base with a salt of its conjugate, right? So this is a very common one in the chemistry lab. And if you change the identity of the weak acid or the weak base, you would be changing the value of the equilibrium constant, the Ka or the Kb. And so you could find a different range of pH. You might have noticed in biology, maybe last year, you might have talked about buffers, and you might have had a pH 3 buffer or a pH 5 buffer, or pH 7, pH 9. There are various concoctions that we could make to have a buffer zone at any point along the pH scale here in order to try to keep the pH at the relatively same level. So NH3 would have a slightly different buffer zone than the acetic acid one we just calculated. One of the most important, in my opinion, for life as we know it, examples of a buffer is in the human body. You guys are probably aware that we need to have our body pH within a certain range. It's slightly basic, right? Just barely basic. And there are actually several systems in place that can kind of govern the amount of H+ ions that we have in our blood at any given point. My favorite is the bicarbonate buffer system because it starts with carbonic acid, and then there's an equilibrium here between the first H that can come off of that and the bicarbonate ion. But it's also related to carbon dioxide gas dissolved in the blood. And we won't go into all the details of that. That's an interesting system to study if you guys major in chemistry, if you take biochemistry in college. That's a really fascinating system, and how your breathing in and your breathing out regulates how much carbon dioxide there is in your blood, which is in turn related to this. You guys know that there's a close relationship between carbonic acid and carbon dioxide. But in order to keep the blood at the right pH so that your proteins stay folded and they don't get denatured and they don't themselves get chemically modified due to the presence or absence of the H pluses there in the solution, a healthy body, a normal system, has a number of buffering systems in place to help balance that. We also see a lot of times prepackaged foods will have buffers added to the liquid, the canned, the liquid in the cans or the jars, as an attempt to try to prevent the food from spoiling, from just maintaining the appropriate pH would help the food to stay preserved long enough for it to have a good shelf life and for us to be able to eat it. Things that we've already said: it has to have a weak acid and its conjugate, or a weak base and its conjugate. They resist a change in pH if you add a small enough amount. Clearly if you added too much, then you would exceed the buffer zone and that would happen. But within a range, they can keep a pH of a solution nearly constant, right, within a small window. And of course, we care about this for life. I do want to talk a little bit about some math for this. So we've got a couple of examples. First, I want to remind you about finding the pH of a solution of a weak acid. Remember, for this, we would need to use an icebox. So let's walk through this real quickly. I know it's your favorite thing to do the iceboxes, so I would hate to rob you of such an exciting thing. Just checking the time there. We're good on time. All right, so if we wanted to know what's the pH of a 1 molar solution of acetic acid, we would do an icebox. We would start with 1 molar and none of those guys. He goes down. They go up at equilibrium. 1 minus X and X and X. Equilibrium constant is the acetate ion and the H plus over acetic acid itself. Then we plug our equilibrium rho into here and also the value of the Ka. So we have 1.8 times 10 to the minus 5 is equal to x squared divided by 1 minus x. Distribute inside, and I get 1.8 times 10 to the minus 5 minus 1.8 times 10 to the minus 5 x is equal to x squared. We get it into the proper format. Don't forget your x and minuses, your plus and minuses. Need to go positive here, negative there. And then that gives us our A, B, and C terms for quad form. All right, you guys, those of you who have it in your calculator, do it. And I'm going to do it as well. So we have a 1, and we have a positive 1.8 times 10 to the minus 5 and a negative 1.8. All right, we get 2 roots here. One's negative and one's positive. The negative one doesn't make any sense, so we have to use the positive one. 0.004234, we'll call it. 0.004234. And then what do we need that for? Specifically in this problem, we need that because we need to know the H plus concentration. So we can stick it into the negative log. So the pH is negative log of 0.004234 and 0.004234. I got 2.37. So pH of a 1 molar acetic acid solution is 2.37. That's just a review. Now how are we going to change it? What's a buffer? A buffer is a mixture of the weak acid and its conjugate base. Conjugate base is here. The weak acid is here. So what a buffer would look like is, scroll down, if we had our same acetic acid solution, but we added a considerable amount of sodium acetate. This is this guy. And so for the first time in my class, we would have an icebox set up where we actually have a concentration initially for one of the products. Now I told you that you wouldn't have to do an icebox like this, and I'm sticking to that. So let me just show you. We would remove an X, add x's. And so what this would do is when we set up the equilibrium constant expression, we would not have x squared on top the way we did up here, right? When you have acetic acid, I'm sorry, that's acetate. When you have acetate times the acid, we had x squared because remember we started with 0 before, but now we're not starting with 0. Now we're starting with 0.5, and so on top, it would be 0.5 minus x times x, and then on the bottom would be 1 minus x. And all of that is equal to 1.8 times 10 to the minus 5. We could still do this. We could still solve, still use quad form, right? It's not that much worse. It's just a little bit more complicated because up here we would have a 0.5x term. So when we did this step here, we wouldn't get x squared and x squared only on that side. We would have a slightly more complicated expression on this side, which would just combine our terms here, but it would change the values of the a, b, and the c. Now, I did tell you that we'll never do an icebox like that, so let me quickly, before you lose patience with me, scroll forward and show you the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is how we would find the pH of a solution that contains a mixture of the weak acid and its conjugate base, or the weak base and its conjugate acid, right? We always have to say. And the way that we would find this is we would calculate the pH. We need this term here, pKa. Remember that is the negative log of the Ka. And then this is a log term, and inside the log is a fraction where you put the initial concentrations of the conjugate base and the conjugate acid. The way that I had this memorized, this is a good way for us because we'll use it. I always remember it's AHA. But I'll give you this equation, and you'll have at least the Ka. I can't say I'll give you the pKa, but you can find the pKa, and I'll give you this whole equation right here. So you'll have these two concentrations in your problem, and then you just plug them in. And I like to remember it is this conjugate base over the acid is AHA, because that, I don't know, it just sticks in my head. But I'll give you the equation. So let's do this for the one above. pH is equal to the pKa, so that's the negative log of 1.8 times 10 to the minus 5, plus the log conjugate base. This guy was 0.5 molar, and the acid was 1 molar. So we put this in our calculator. I actually already calculated that out, didn't I? Let's look back up here. It was 4.74, the pKa of acetic acid. So we have 4.74 plus, and then we're going to have to punch this in. So the log of 0.5 divided by 1, so that's just 0.5. I got negative 0.30103, we can call it. And so when we combine that with 4.74, what do you get? I got 4.44. 4.44. So let's think about that pH for a second. Does that number make sense? Does that number make sense? So when we did, scroll up, we did this calculation, we found the pH of just acetic acid, 1 molar acetic acid is 2.37. And then notice when we added a fair bit of the base, we increased the pH. Remember that pH is kind of inversely telling us about the H plus concentration. So a higher pH means a lower H plus concentration, and that does make sense because when we added the conjugate base there, it would shift the reaction to the left. We would use up this guy just as we use up that guy to try to rebalance the equilibrium. So yeah, it does make sense to have a pH of 4.4. Let's do one more example. So we have the same buffer system, acetic acid and sodium acetate. So there's our conjugate base, or the Ah, if you're remembering the AHA, and this would be the Ha, right? That's our weak acid. And so pH is equal to pKa plus the log of AHA. All right, conjugate base on top, 4.74 plus the log of 0.3 divided by 0.2. I'll punch that in your calculators. So we've got this number, I got 0.17609. So we're adding that to 4.74. I got a pH of 4.92. Pretty quick way to do that calculation. The longer way, of course, would be to go to an icebox. And let's go ahead and do that. We should go ahead and just practice one more time doing an icebox, because you'll need to know how to do this. So the reaction here is the acetic acid ionizing. If no salt were present, then we would just have the 0.2 molar. And these guys would just be X. And so our Ka is 1.8 times 10 to the minus 5. Am I remembering that right? 1.8 times 10 to the minus 5. And that's going to be equal to x squared divided by 0.2 minus x. Multiply both sides. We need to multiply 0.2 times 1.8. Get, I guess I could have done that in my head. 3.6 times 10 to the minus 6. Oops. Minus 1.8 times 10 to the minus 5x is equal to x squared. Bring those buddies over. Plus minus. Quad form. 1x, that guy, and then this is different. We have 1.8, no, 3.6 times 10 to the minus 6. Again, we have a positive and a negative. We won't use the negative, so we have 0.001888. So, x is 0.001888, and that is the molarity of the H+. So now we can find the negative log of that value. And I got 2.72. Is that a reasonable pH? Sure. When we don't have the conjugate base present, the pH would be significantly lower. And if we look back to compare it to the very first one we did, we found 2.37 for a 1 molar solution. And on a log scale, I mean, 0.2 is considerably smaller than 1, and 2.37 is not considerably smaller than, that's a 2, than 2.72. But on the log scale, remember, logs sort of behave a little bit differently. They're exponents. So I think this is a totally reasonable value to get there. That's it. That's it, guys. We finished the notes. We finished the unit. We finished the year. Everything is done. It's all on you now. So my plan has been for us to have a couple of review days to make sure that we're all caught up. You can be working on your lab. You can be working on your packet. If you're watching this video, that probably means that I'm not there. But if I am there, then of course we'll just keep on keeping on. But if I'm not, then the other chemistry teachers are your best resource. Mr. Collins and Miss CP have volunteered to step in and help at lunchtime, answer whatever questions you guys have. And of course, I can at times be in touch with them or with you for extra help. But anyway, keep up the good fight, guys. See you later.